So in the last video, we introduced or maybe reintroduced the concept of maximum likelihood estimation and really focused on the idea of the likelihood function. Now, again, let's do a quick review. So having observed data x1 up to xn from, let's say, some distribution with density f theta, f given theta, so f of x given theta, then the likelihood function is nothing but the joint distribution of all the observations given theta. And in the event that the random variables drawn are independent of each other, then you have product I going from 1 to n, f of xi given theta being the likelihood function. And what this measures is it measures how likely is a value of theta given the data that we've observed, which means to say that, okay, well, if this was the value of theta, what is the chance that I would have seen the data that I have seen? And you do this for all observations and you take a product and that becomes the likelihood function. Right? Okay, so that now what we'll do is we also motivated that once you have a likelihood function, let's say a function like this, it's a function of the thetas themselves, and on the y-axis here you can have likelihood, or often it's easier to look at the log of the likelihood. Then the value of theta that is most likely as the maximum value of the log likelihood, that corresponds to your maximum likelihood estimator. Okay, so what we want to do now is go through a few examples of this, of actually implementing this and studying this. So let's look at Bernoulli random variables. So what I have are data x1, x2 up until xn that are from IID, so independent and identically distributed from a Bernoulli distribution with probability of success P, where I'm going to assume that P is anywhere between 0, 1 and inclusive. Okay. Now then, in this case, the likelihood is nothing but, recall, it is nothing but P given the data that I have observed. So L of P given the data that I have observed. Now it is nothing but the product of the joint distribution of the product of each of the individual xi's given P is in the probability mass of that. Now I realize that I should write this as the probability of xi is equal to small xi given the probability P. So that's what the notation P here is a shorthand for. Okay. Now once I do this, well, the PMF or the probability mass function of this is nothing but P to the power xi times 1 minus P to the power 1 minus xi. Right? That, we recall, is the PMF of a Bernoulli random variable. And that's exactly what we substitute in the next step here. So we just substitute P to the power xi, 1 minus P to the power 1 minus xi, right? And I can now use the product inside and turn the common P base becomes P to the power summation xi, and 1 minus P to the power n minus summation xi. Please remember this n because often students mess up realizing that there should be an n here. Okay, so this gives us the likelihood function. Now to obtain the maximum likelihood estimator of P, we want to maximize this likelihood function. We want to find the value of P that gives us the largest value of the likelihood. But maximizing the likelihood is equivalent to maximizing the log of the likelihood, right? So the argument that maximizes the likelihood is the same argument that maximizes the log likelihood. But taking the log, as always, makes our calculations much, much easier. So L of P then becomes log of capital LP given x. So I take log. And once I take log, well, P to the power summation xi, the summation to the power comes over here. I get log P. Similarly, I get n minus summation xi log of 1 minus P. Okay. Now I'm set up. I have my actual log likelihood function. And what I'm going to do now is, because I want to maximize it, in order to maximize a function, I know that I can look at the first derivative And if this is, let's say, if this is, let's say, my function, the derivative over here is nothing but the slope of the tangent line, right? And at the maxima, the slope here, slope of this line is equal to 0, right? So if I take the derivative of this function and I look at the slope everywhere and find, well, what value of x, at what value of x is my slope equal to 0? That is the value of x that I want, right? But we have to be careful that the slope of the line can also be 0 when there is a minima, right? Here also, the slope of this line is 0. But I don't want a minima, I want a maxima. I want the maximum of the log likelihood, not the minimum of the log likelihood. So if I want to avoid this, I want to check, okay, well, the slope is 0. That means the first derivative is 0. But then also the second derivative over here, because this is the because this is the shape of my function, the second derivative over here, L double prime theta, should be negative, right? Or not theta, well, L double prime P should be negative. If it is, then I know I have a concave function and not a convex function. Okay, so these are the steps. So the first thing I want to do is I want to find the value of P that actually gives me a slope of 0, right? So which means that I first find all the slopes. So I first find what are the different slopes for various values of P, which means I take the derivative. So over here, the derivative gives me summation xi divided by P minus n minus summation xi divided by 1 minus P. And I set it to 0 because I want to find that which of the slopes, all of these slopes, which value of P gives me 0 slope. Okay, and once I set it to 0, I very quickly see that that value of P that gives me slope 0 is P hat being equal to summation xi by n. Okay, so I get that the place where the maxima could potentially have occurred is at the average of all the observations. So this is the probability or the proportion of ones in my Bernoulli random draws that I have. Okay, but I don't yet know if this is a maxima or a. I can only know if it's a maxima or a minima based on what type of shape does this actually take. Okay, so in order to understand that, I want to know what kind of shape does it take, which means I take the second derivative. And once I take the second derivative over here, well, I take another derivative of this equation. So I get minus summation xi by p squared minus n minus summation xi by 1 minus p squared. Now both of these, this term is also negative and this term is also negative. So both of these terms are less than 0 irrespective of the value of p, which means everywhere this function is indeed have a negative second derivative, no matter what the value of p is, which means I do indeed have a maxima, right? So we discussed last time that this means that the function is concave, which means that p hat is in fact a global maxima. Okay. Now, it's possible in some examples I do not end up actually checking the second derivative condition because it's either a bit too complex or it's maybe not the best use of our time in these videos. And if I do skip it, then I would expect you to check it for yourself. Right? So the act of checking whether a second derivative is negative or positive, or maybe neither, is something I would expect you to do. Okay, so thus we get p hat MLE is the average of the observations. Okay, so that gives me a maximum likelihood estimator, which means that if I have, or maybe I should go back here. So this means that if I observe x1 equal to 1, x2 equal to 0, x3 equal to 0, x4 equal to 0, and let's say x5 equal to 1, these are all my observations from Bernoulli P, And I want to ask, wait, what is the probability of success that I've actually found these ones and zeros? What you would do without doing any maximum likelihood estimation is you would guess number of successes divided it by 5, which is your proportion of success, right? That's exactly what your guess of p hat should be, probably without knowing Emily. But the number of successes is basically exactly the same as summation of xi, I going from 1 to n. Because when xi is not a success, it is 0. Right? So number of successes is exactly equal to summation xi. And so this is nothing but p hat, Emily. So without knowing what you'd guess for your actual estimate of the probability of success would be the maximum likelihood estimator, the estimator that gives you the largest likelihood of a particular value. Let's move on to another example that may not be as easy as our previous one. Okay. This is that this is that of the density of a two-parameter exponential distribution. Okay, so a two-parameter exponential distribution has density f of x given mu and lambda. So when I write given mu and lambda, I'm indicating that the parameters of interest are mu and lambda. Okay, this density is lambda e to the power minus lambda times x minus mu. Okay, now the support of this density is that x has to be greater than or equal to mu, and mu needs to be in all reals, and lambda is positive. Okay, so the support of x is bounded below by mu, so it cannot exceed mu. Sorry, it cannot exceed mu on the negative side. But mu itself can be any number in R, and lambda has to be positive. Okay, and something I missed over here is I assume I have x1, x2, xn, IID from this distribution. Okay, so I assume I actually have data from this that I've observed. Okay, now that I've observed data, I can find the likelihood function, very similar to the way I'd done before. So the likelihood then is L of lambda comma mu given x. And now there are two parameters that I'm interested in. So it's a two-parameter likelihood function, which means if I were to draw this likelihood function, I'll have mu on the x-axis, lambda on the other axis, and on the third axis over here, lambda on this axis, and on the third axis would be lambda mu given lambda of mu, L of mu comma lambda given x, right? And that would need to be constructed in a three-dimensional space. So the two dimensions are the sort of the various values of mu and lambda that can be taken, and for this value of mu and lambda, there will need to be some let's say likelihood function value. Okay, some likelihood function over the two-dimensional parameter space. So I'm not really a great drawer of these things. Okay, so L of lambda given mu comma x is then nothing but the product of t going from it should be I, not t. I going from 1 to n f of xi given mu comma lambda. So it's just the joint density. But now I can actually plug in what f of xi's are. So that is nothing but lambda e to the power minus lambda xi minus mu. Indicator xi greater than or equal to mu. Now this indicator is really, really important because notice that this is a function of lambda and mu. And the support is a function of also the parameter mu, which means the support of the function, because the likelihood function does depend on the parameter mu in its support, that also needs to be a part of the likelihood function. Okay? Because if I take a value, if I look at mu such that mu is actually not such that xi is greater than or equal to mu, then the likelihood there is 0. So that value of mu is not likely at all. If I choose a value of mu that's actually less than any of the xi's. right? So then this is nothing but, I can take, well, this product I can just write as lambda to the power n because it's just a constant. And I can take the product inside to make this a summation. So I get e to the power minus lambda summation xi. And then this mu with the summation becomes n mu. But then also this indicator has to hold for all the product over I, which means it has to hold for all xi's. So each of the individual xi's has to be greater than equal to mu, which means I get the indicator that all the xi's have to be greater than equal to mu for all mu and for lambda positive. But notice that if all of the xi's are greater than equal to mu, if every single value of the xi, all the data points are larger than some number mu, then that means the smallest of those xi data is also larger than mu. And these are equivalent statements, right? So I should actually put it, right? So if the smallest value of the xi's is greater than mu, then that means that all of the data is actually greater than mu. And further, if all of the data is actually greater than mu, then this implies that the smallest xi is greater than mu. So these are equivalent statements, which means I can replace all of the xi is greater than equal to mu to just the minimum of the xi greater than equal to mu. Okay. Okay, so then this becomes our log likelihood now. Now, why was this trick useful? The reason this trick is useful is now what I want to do is I have my likelihood, and now I'm just going to basically look at the following object. So let's go back. I want to now maximize this as a function of lambda and mu, right? So as a function of both lambda and mu, want to maximize. But now let's look at this as a function of mu itself, just mu. Now mu occurs here and mu occurs here in the likelihood function. Okay. Now this thing as a function of mu, so let me just erase this so I can write something here. So this thing as a function of mu is nothing but lambda to the power n, e to the power minus lambda summation xi. That part doesn't have mu. And then e to the power lambda n mu. Okay. And then the indicator that the minimum of all the xi's is greater than equal to mu. Okay. But now this is one part that has mu and this has the other part that has mu. If I just look at this part, the first part, if I just look at the first part here, then lambda is positive, n is positive, and mu is whatever it is. But these two are positive. And so what I have is the exponential function e to the power, this is e to the power lambda n mu, where on the x-axis I have mu. So it's some exponential function, which means that it is a forever increasing function. Okay, right? It's a function that keeps on increasing. So if I want to maximize the likelihood, this will get maximized at the largest value of mu because it's a forever increasing function. But lucky for us, the largest value of mu, because mu is less than equal to minimum of xi, right? It cannot exceed the minimum of all the observations, which means that the largest value of mu that it could have seen is minimum of all of the xi's, right? So the largest value of mu that's actually possible is actually minimum of xi's. That's the largest value that the likelihood that mu can take. It can't take any values before that, after that, because if it does, then after this, it just becomes the likelihood function just drops down and just becomes zero after that because of this indicator function, right? So the likelihood function goes up like this, and then as soon as it reaches mu equals minimum of xi's, it becomes zero. So the largest value it can take happens here, which is nothing but minimum of xi's. which means that the maximum likelihood estimator of mu is the value at which the likelihood is maximized, which is nothing but minimum of xi's, which is also denoted as x order 1. Okay. Okay. That is our maximum likelihood estimator of mu. We haven't as yet looked at lambda. Remember that also is a parameter. So now I take my maximum likelihood estimator of mu and I put it in my likelihood function because we've already gotten its best value. So L of x1 comma lambda given x now is lambda to the power n e to the power minus lambda summation xi minus n order xi. Now again, at this point, there are no restrictions on the values of lambda, so I can actually try and take a derivative in the usual set to 0. And what I also note is that this is a little bit of a complicated looking function to take a derivative of, so I'm going to take log. So once I take log, over here, I get n log lambda minus lambda and this part. Okay. Now that I've taken log, I have a function. I want to find where is its slope equal to 0, which means I try and find the slope everywhere and then find for what value of p is that slope equal to 0. Okay. So I do this, take derivative, well, this is just n by lambda minus summation xi minus n x order 1, and I set to 0 to find at what value of lambda do we actually get the maxima. Okay. But before I do that, I can set to 0 and solve it. I wanted to know whether I'll get a maxima or a minima. And I take another derivative. This is a constant, goes away, and this becomes minus n by lambda squared, which is always negative, which means I again have a concave function, which means again there's a global or unique maxima. Great. I set this to 0, and then I see that lambda hat MLE is nothing but n divided by summation xi minus n x order 1. Okay, so I have my mu hat MLE and my lambda hat MLE. Both MLEs are available to me. So these are two instances of maximum likelihood estimators. We'll do a few more in a slightly different context. But before we proceed, it's good to ask ourselves why MLE. Hopefully the logic of maximum likelihood estimators is clear. But why exactly MLE? Aren't there other ideas or other ways to estimate different parameters like lambda and mu that might have good properties? So one of the reasons of using maximum likelihood estimator is that it often, maybe not always, but often MLEs are consistent and asymptotically normal. That means in general, again, not for all problems, but in general, for some likelihood L of theta given x, under some certain conditions, theta hat MLE will converge to theta in probability as n tends to infinity, which means if you keep giving me more and more samples, theta hat MLE from those samples will converge to the actual value of theta. And then under some other conditions, some additional conditions, we also have that as n tends to infinity, square root n times theta hat MLE minus theta, this quantity converges to normal 0 comma sigma star, right? Which means not only do I have a convergence of just theta hat MLE, I also have a convergence at root n rate of this quantity to a distribution, which is normally distributed, centered at 0, and sigma star is some estimable matrix. It's a matrix that we can typically estimate, and it's called the Fisher information matrix. More specifically, this Fisher information matrix, sigma star, is I theta inverse, okay, which I theta is minus of the expected second derivative of log of fx given theta. So let's understand this for a second. So a log of the second derivative of the log is essentially looking at your curvature of the target log likelihood function. Right? For example, if the log likelihood function is like this, okay, versus if the log likelihood function is like this, okay. So this quantity over here measures exactly what the curvature is at this point, okay. That's what I theta measures, okay. So but it's not just the curvature for any one given data point, it's the expected curvature for any given data point. Because like we discussed in the last video, the likelihood function is a random quantity because the data that we are getting is also random, right? So if X is random, then this is a random quantity, which means we typically get, multiple types of likelihoods. Then you average them and you get one curve, right? So that's the expected log likelihood, and here you have the expected log likelihood. Now, I theta, this Fisher information, essentially measures the expected curvature at the true maximum. So what is the expected curvature at this point? Okay. If the second derivative is large, so if this quantity is large, that means that the likelihood function is sharper near the truth, right? So if this quantity is large, then this corresponds to this part over here. Okay. So here I theta is large and here I theta is small. Okay. So if the second derivative is large, then the likelihood function is sharper near the truth, implying less variability in the MLE. Again, we discussed this in the last time. If this is what the expected curvature is, right, then I would expect only maybe this much amount of variability in my MLE. Versus if this is the expected curvature, then I might expect, a little bit larger amount of variability, right? Okay, and this is really what I theta interprets, and then because the actual variance is an inverse function of I theta, sigma star is I theta inverse, which means it actually is inversely proportional to the amount of curvature. Okay, so if we use MLE estimation, okay, after ensuring that there are some, important conditions that are satisfied that guarantee us consistency and normality, we can use it to understand our variance of the estimator. We can also use it to maybe construct confidence intervals around our estimator. And that's really going to help us in inference. Okay. Now, I haven't talked much about, consistency of the estimators themselves and sorry, the conditions required for these results, and they're quite critical, something we won't be able to go over in this course. But if you're interested, a course on inference would be really useful to understand context about that. Okay. All right. So in this video, we're going to limit ourselves to here. In our next video, we're going to look at other examples of maximum likelihood estimation motivated via linear regression or regression.